Welcome back. In this second video, we'll just take a look at some applications of working with logical statements. And logical gates are really powerful. They're used in electronics and infrastructure of computers. Very, very powerful stuff that many of you have or will be studying. So in digital circuits and Boolean processing, so Boolean just means named after George Boole, who was sort of the father of this type of logic, where output is either true or false. We use logical gates. These are symbols representing the various connectives below. Most often these symbols are used in electronics. However, because they are logical symbols, their uses are virtually unlimited. By the way, in electronics, these types of gates are built using transistors, and it's really, really cool to see how the very first logical gate was built, where essentially it would, depending on what the signals were on the input, would result in a certain action taking place on the output. So the cool part is that these logical gates act just like our logical operators. So for example, as an OR gate, if I look at an OR gate has two inputs. In this expression, I don't have to draw it again, there are X and Y, but these X and Y labels could be anything. So you give it two signals, one which is, we'll call X, and one which is Y, and then what comes out is X or Y. So usually we think true or false. Sometimes instead of using true, we use 1. Instead of using false, we use 0, and that's often the greater convention in working with digital circuits. And so what happens here is you have two signals, and in terms of electronics, we can reduce a signal to just being high or low. Basically, it exceeds a threshold, and then that means the signal is high, or it doesn't exceed the threshold. There's a really low voltage, and so, or no voltage, and the signal is false. So instead of using false, false, or false, true, I'll use 0, 1, 0, 1. So think of these as acting as true or false. And then 0, 0, 1, 1 for false, false, true, true. So if we receive a 0 on both inputs, so these signals could be coming from some sort of generator or some sort of multiplexer, or it could be coming from any one of many, many locations. If both of these are zeros, well, that's false, false, and this is an OR gate. So the only situation under which it will output a high signal or a current on the output side is if X or Y is satisfied. So if both inputs receive a 0, then there's a 0 output. That's a false. And if any one of the inputs is a 1, if I had a 0 here and a 1 here, then that's going to output a 1. If I have a 1 here but a 0 here, it's an OR gate, so it'll output a 1. If both of these are a 1, it's an OR gate, so it'll output a 1 as well. So an AND gate operates under the same principles. An AND gate, its purpose is to only output a high signal if both of the inputs are 1. So if both of these guys are 0, corresponding to the first row, there's no signal on the output. If we have a 0 on one input but a 1 on the other, it's an AND gate, so that's going to be a 0. If we have a 1 and a 0, same situation. And then if both of the inputs are high, then we're going to get a high signal on the output. And finally, for a NOT gate, or an inverter, some people refer to this as an inverter, that's just going to take an input and output the opposite signal. So it's basically a negation operator. Sometimes you'll see it X prime, or you can write not X, or sometimes we'll see X with a bar over it. So to be consistent with this notation, let's just stick with X prime. So that's, again, the same thing as not X. And so all that will do is if X has a 0, then it's going to output a 1. So X is 0 in both of these first two lines. So to invert that signal, it will negate those values, make them 1s. And anytime there's an input of 1, the output value will be a 0. So that's why we call it an inverter. It inverts the signal. And with these 3 gates, we can pretty much build any other gates and fabricate a whole lot of other types of equipment. But let's just sort of model with this, and let's see how we could take a situation and build something useful. So the sensitive electronic equipment in the control room of a recording studio needs to be protected from both high temperatures and excessive humidity. An air conditioner is provided that must go on whenever either the temperature exceeds 80 degrees or the humidity exceeds 50 degrees. What is required is a control device that has 2 inputs, one coming from the thermostat and one coming from the humidistat, and one output going to the air conditioner. It must perform the function of turning on the air conditioner if it gets a yes signal from either of the input devices, as summarized in the table that we're going to build. Draw the logical gate that should be used, its input signals and output signals. So first of all, it's going to be useful to define some variables here. So let's define T to be the signal, or to be the maybe even a statement. The temperature exceeds 80 degrees. And that value could be true or false, yes or no. H will let be that humidity exceeds 50%. Okay, so I'm going to build a truth table, and before I evaluate what combination or how these 2 signals are going to be combined, let's just plot out all the different possibilities. So we could have 0, 1, 0, 1, 0, 0, 1, 1. So this means that if T is 0, that means that the temperature does not exceed 80 degrees, and the humidity does not exceed 50%. And we need a control device that has 2 inputs, one coming from a thermostat and one coming from a humidistat, and one output going to the air conditioner. It must perform the function of turning on the air conditioner if it gets a yes signal from either of the input devices, as summarized in this table. So if the temperature is still pretty low, and the humidity is still pretty low, then the AC has no reason to turn on. If the temperature is below 80 degrees, but the humidity exceeds 50%, we want to turn on the thermostat. We want to turn on the air conditioner. We want to send a 1 signal to it. So here we can kind of visualize it like this. We have 2 inputs. We have T, we have H, and then we're going to have 1 input or 1 output, which is going to be what's sent to the air conditioner. So we'll say this goes to the air conditioner. So we'll continue building this. So if the temperature exceeds 80 degrees, but the humidity is below 50%, we want the thermostat, the air conditioner, to be given a signal to turn on. And if both of these things happen, definitely we want that AC to turn on. Now we see that if any one or more than one of the signals is a 1, the output is a 1. And we recognize that to be a disjunction of T and H. So that's going to be an OR gate, and an OR gate is drawn as described in this picture. It has this almost like an arrowhead looking shape to it. So what we want is we want an OR gate in between here. And it's going to take T or H and output that signal, and that's what's going to go to the air conditioner. So we've just applied the Boolean logic to building a logic circuit that will do this for us. And then if we wanted to actually execute this and build this controller, we would play around with transistors or get the right logical circuits to build it. Now, when we combine logical gates, we create what is called a combinatorial circuit. So if you have 3 or 4 gates in there, you have a combinatorial circuit. Let's take a look at another real-world example. A home gas furnace is attached to 2 thermostats, one in the living room area of the house and the other in the chamber where the furnace heats air to be circulated. So it has 2 thermostats, thermostat 1, thermostat 2. if the first thermostat senses that the temperature in the house is below 68 degrees, it sends a signal to the furnace to turn on. On the other hand, if the thermostat in the heating chamber becomes 1 degree hotter than 150 degrees, it sends a message to the furnace to turn off. This signal is for reasons of safety and should be obeyed no matter what message the house thermostat is sending. So we kind of have this override switch that if the thermostat in the furnace is getting too hot, then we've got to turn off the furnace. And even if it's cold inside the house, if it gets too cold, like 65 degrees, but it's 152 degrees on the thermostat in the heating chamber, we, for safety reasons, have to shut it down. So let's try to draw the circuit for this circuit. Let's try to draw the circuit for this system. So first of all, we have to think about what we have. We have two thermostats, and the first thermostat senses the temperature in the house. So I'm just going to call this signal H. H is I'll actually write this as the temperature in-house is below 68 degrees. Okay, so a signal of 1 would mean yes, it is. 0 would mean no, it's not. Then I have a second signal, and that one's to the furnace, or the thermostat in the furnace, so I'll say F, and that is the temp in heating chamber is greater than 150 degrees. And again, 1 will represent yes, 0 will represent no. So I can build a truth table for this based on the situation being described, and I can figure out how I want to build this. All right, so here I have H, here I have F, and I'm just going to look at all the possible pairings. I could have 0, 1, 0, 1, and here 0, 0, 1, 1. Now I don't know what the logical operation here is, but I know that I want this to be the signal that's sent to the furnace. And we'll define that 1 means to turn it on, 0 means to turn it off. So, okay, here we're saying that no, the temperature in the house is not below 68, and no, the temperature in the heating chamber is not above 150 degrees. Therefore, we have no reason to do anything. We don't want to take any action. We don't want to send any signal to the furnace because it's comfortable in the house and there's nothing going wrong with the heating chamber. So just keep it off. Then if here we have the furnace reaches or the heating chamber has a temperature that, yes, is above 150 degrees. So no matter what the H signal is, we want this to be 0. And if it is the case that the temperature in the house drops below 68 degrees and the temperature in the heating chamber is not above 150, then go ahead and turn on the furnace. Finally, if it's the case that the temperature drops below 68, but the furnace is overheating, we want to make sure, or the heating chamber is way too hot, we want to keep the furnace off in that case. So there's only one situation in which we want the furnace to turn on, and that is the situation in which H is 1 and F is 0. So how do we build something where there's only this one situation where we have an output of 1? Now that's not but it isn't an AND gate, because an AND gate would be for H and F, we would require both the inputs to be 1. However, if we look at this row here and we think about what must happen if I were to use an AND gate for only this row to output a 1. Well, I would require h to be true, right? So if h was a 1, then that would mean h is true. And, well, I can't put f here because if I said h and f, the furnace would turn on in a situation where it shouldn't turn on. But if f is 0, that means not f is 1. And in this row, h is 1, f is 0, but not f is 1. So this will return a 1. So what I want in order to build this is if I don't have a simple expression for the truth table I've generated, I could just look at the rows that contain a 1 and generate an AND gate based upon that. So this is actually what we call a minturn, And a minturn applies to any row in which you write an AND expression to generate a 1 signal. So in order to generate this 1 signal, I'm going to need 2 inputs. I'm going to need H and F. But I will require for the F signal, I will need that to be inverted prior to inputting that into an AND gate. Because I want to make sure that when F is 0, it sends a 1 to that AND gate. So to draw a NOT gate, that's just a triangle. So what we'll get here is a NOT gate or an inverter. And so what will end up coming into this AND gate, what will end up coming into this AND gate is a signal H. F is what's coming into the NOT gate, but what comes out of the NOT gate is an F prime. And here I'm using the negation operator, but that would be the same thing as F prime. So let me just be consistent and erase this and write this as F prime. Again, means the same thing as not F. And so then what comes out of this AND gate is H and not F. And that's exactly what I wanted. So you can see that if say a 1 signal comes into H, but a 1 signal also comes into F, well, that means the 1 signal, so if I put a 1 and a 1 in here, then a 1 comes into the AND gate, but a 0 comes in from the other terminal because that 1 signal gets inverted, and 1 and 0 will produce a 0 on the output side, which is exactly what I would want if the temperature in the house is below 68, but the temperature in the heating chamber is above 150. All right, and here's another example of a combinatorial circuit. We want to write an expression for this. Well, how do we go about doing that? In order to do so, we're going to label all of the terminals. So X, Y come into here, and that means X or Y is going to be the output of that signal. Now that's going to get inverted when it comes through the inverter, so whatever X or Y is, that is going to be inverted. And remember, that's just like the negation operator. I could put the negation operator here out front. Now, here I have an AND signal, so I'm waiting for another signal to come in. I have to determine what that is. So I'm going to start back here at this next branch, and here I have Y coming into an inverter, so I'll have Y prime coming into the OR gate, and X will get ORed with Y prime. So this will be X or Y prime. Now it's not X or Y all primed. X is not getting negated. It's only Y getting negated as the input. Now here I have an OR gate, but I'm waiting on another signal. That signal is Z. So on the output of this OR gate, I will have X or Y prime. That's this input, ORed with Z. And so what these two signals are coming in here will get conjoined together. So X or Y prime, that's this input, and this input, which is X or Y prime or Z. Now guess what? I could use a series of logical operations to reduce the complexity of this circuit if I wanted to, and to see, can I do this with fewer gates? So that's another reason why we want to reduce this in order to get fewer gates. So reduce using laws to possibly get fewer gates. In our last example, a garage light is to be controlled by 3 switches, one inside the kitchen to which the garage is attached, one at the garage door, and one at the back door to the garage. It should be possible to turn the light on or off with any of these switches, no matter what the position of the other switches are. Design a circuit to make this possible. So the 3 inputs are the 3 switches, which we will label 1 or 0, according to whether they are in the up or down position. We will design a circuit that turns the light on whenever the number of inputs equal to 1 is odd, since flipping any switch will change whether this number is odd or even. We want a circuit with the following truth table. So imagine that, to kind of explain this a little bit better, let's say we have these 3 switches, and what's going to happen is if right now this one is on and these guys are off, then I want the light to be on. So here's my light bulb, and this is a light bulb here, and we want this to be a 1 whenever that one switch is on. But now if I were to turn or flip another switch into the on position, that means this light should now turn off. And if I were to flip this third switch on, if I were to make this a 1, then this light switch should now turn on again. So what that means is that if the number of inputs equal to 1 is odd, we want the light on, but whenever the number of switches on is, the switches and in the 1 position is even, we want the light to be off. So let's go ahead and design that truth table. And here's what our truth table will look like, and we'll build the circuit for it. So we'll have our 3 signals. We'll call this, I'll use S1, S2, S3 for these 3 switches. And now we want to build this truth table for S1, S2, S3. So here's my truth table for S1, S2, S3. And to look at all the combinations of these, we're going to have 8 of them. By the way, if you look at 2 to the third, you're going to have 2 possibilities for each switch multiplied by the 2 possibilities for the second switch multiplied by the 2 possibilities for the third switch. So there are 8 different positions that you can have. And as long as you list them out as false, true, false, true, false, true, false, true, and then list this out as false, false, true, true, false, false, true, true, and this last one as 4 falses followed by 4 trues, you'll have hit every single possibility. So here is what we want the light to do. We said that as long as there's an odd number of switches on, we want the light to be on. So we could have used 1, I don't know why we use falses and trues here. Let me use 1s and 0s. Okay, so if all of the switches are off, what do we want to happen? Well, we'll design a circuit that turns the light on whenever the number of inputs equal to 1 is odd. Well, that's not the case here, so we don't want the light to turn on. Now somebody flips switch 3, light pops on. If they switch on just switch 2, light pops on. If switch 2 is on and then switch 3 is flipped on, we want the light to turn off. And just if there's any situation in which there's an odd number of switches, then we want the light bulb to turn on. Now once again, this is not very obvious what combination of these 3 signals we want to have in order to create this circuit, so we'll build these minturns. And that means that we'll look at only the rows in which we want the light to turn on, which is there, 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 and there. And in this first one, we see that if S1 is 0, then S1 prime will be 1. And if S2 is 0, then S2 prime will be 1. And if S3 is 1, then S3 is 1. So this will be a 1, 1, 1. That will model this second row. And then here I'll have S1 prime on, S2, S3 prime on. And here I'll have S1 and S2 prime and S3 prime. And in this last row, this is just S1, S2, and S3. And then we want the light to turn on in any one of these situations, so we want an OR of all of these signals. So if I have my S1, S2, S3, so here I will draw S1, S2, S3, and if I wanted to draw this circuit, I would first of all need a situation where I feed these through an inverter to get S1 prime, because I'll need that. I'll also need S2 prime, and I'll need S3 prime. And now I know that if S1 prime and S2 prime and S3 get used together, then that should turn the switch on. So I'm going to kind of branch this out over here and put this into an AND gate. S2, same thing, S2 prime. And then I want an S3 into there, so I'm going to go grab an S3 over here, basically attach a wire before the inverter gate and run that up here and have my AND gate that's going to AND those three signals together. And then I also want S1 prime and S2 and S3 prime, so I am going to grab S1 prime. I'm just going to draw a little hoop over here to show that those aren't connected. That'll go into a gate. And S2, so I'm going to need to grab a S2 signal from before the inverter. And again, I'm going to drag that out over here. You can see it's getting kind of messy. Put that in there. And then I also want S3 prime, which is, thank goodness, the signal here, and AND those together. So what I'll get on this output is S1 prime and S2 prime and S3. And these are all going to go into an OR gate. Now I can have an OR gate with 4 inputs. It will be an exclusive OR because we know that more than one of these things can't happen at the same time. You can't have switch 3 in the on position and simultaneously have it in the off position. So this will by virtue naturally be an OR gate because these things simply can't all happen. So here I'll have my S1 prime and S2 and S3 prime. And so I'll kind of do the same thing for the other 2 situations and run signals into that AND gate that we're building here. Whoops. And then we'll run this signal here, and we'll run this signal here, and then we'll OR those signals together, and then we'll get that output that goes to the light. And the next question that we normally want to ask, we're not going to address this here, you get this in a digital circuits class, but can we simplify this circuit? Do we really need so many wires and so many gates in order to be able to do this? And the answer is we could reduce this. We often use something called K-maps or Karnaugh maps, but we're just not going to get to that in this class. So that concludes our lesson for this week.